Ever find yourself stuck between a couple options, like, trying to decide, should I take the highway or back roads to work? Or maybe, is that new restaurant worth trying?
We face these little dilemmas all the time.
Yeah, and sometimes it feels like the only way to decide is to just flip a coin, right? I mean, heads I do this, tails I do that.
It's that fundamental uncertainty, almost like rolling a die and waiting to see which number comes up.
Yeah.
That anticipation of what's going to happen.
Exactly. That not knowing. Well, there's a whole branch of math dedicated to not just experiencing that uncertainty, but actually understanding it, breaking it down. It's the world of probability. And
Yeah.
that's what we're diving into today.
And what's fascinating is that beneath what seems like pure chance, there's a structure, a
Yeah.
logic that probability helps us uncover.
Right. And for this deep dive, we've got some great learning material that lays it all out. Now, don't worry, we're not going to get bogged down in a bunch of complicated formulas.
This is about making these ideas click for you.
Yeah. Think of it like this. This is your express lane to understanding how likely things are to happen. Clear, straightforward, and hopefully even a little bit mind-blowing.
Because when you grasp these core principles, you gain a tool for navigating so much of life. From making sense of data to making informed decisions when you're not totally sure what's going to happen.
Absolutely. So our mission for today is to really distill the essence of what's called theoretical probability. We want to make these ideas not just understandable, but maybe even a bit surprising. And you'll walk away with a solid grasp of this fundamental concept without having to wade through tons of information.
And our source material very wisely starts with something super basic, the ideas of randomness and equally likely outcomes.
Okay, so going back to that coin flip, if we want to apply probability to this, we got to imagine an ideal coin, right? Perfectly balanced, no weird weights or anything that would make it more likely to land on one side than the other.
Right, a fair coin.
Exactly. And when we talk about a random toss, we mean it's got to be a fair flip. No sneaky tricks to influence how it lands. In this perfect scenario, heads or tails each have the exact same chance of coming up.
And we can extend that same idea of equally likely possibilities to other simple situations, like rolling a standard six-sided die, what our source calls a fair die. So each of those faces 1 through 6 has an equal chance of landing face up.
So in theory, you've got an even shot of rolling any of those numbers.
Precisely.
But here's a really important point, and our material highlights this right away. Not everything in life works with these perfectly balanced odds. Think about that bag of marbles we've talked about before, the one with 4 red marbles and just 1 blue one. If you reach in without peeking, would you say it's equally likely you'll grab a red or blue marble?
Obviously not. With more red marbles, the chances of picking a red one are much higher. And our source makes a key distinction here. The overall action of the experiment is drawing a marble, but the specific results, red versus blue, don't have the same probability in this case.
Right, because the setup isn't perfectly balanced.
Yeah.
And our material is very clear that for now, we're going to focus on those scenarios where we can assume a level playing field, where every possible outcome has an equal chance. That's our starting point for really understanding probability.
And this focus on equally likely outcomes but let us make a huge jump from observing what happens over many repetitions, what's called empirical probability, to the power of theoretical probability.
So with empirical probability, it's all about doing an experiment over and over and seeing what happens, like flipping that coin hundreds or even thousands of times and noticing it lands on heads roughly half the time. That gives you an estimate of the probability.
Right, but as the source points out, there are limits to that approach. Imagine trying to figure out the probability of a satellite launch failing.
By launching a ton of satellites and seeing how many crash? Not exactly practical.
Not to mention incredibly expensive and time-consuming.
Right.
Or trying to predict building collapses during earthquakes by, well, waiting for a bunch of earthquakes to happen.
Definitely not the best way to gather data. So theoretical probability offers a different path. We make those key assumptions like all outcomes are equally likely, which lets us calculate probabilities directly. No need for endless trial and error.
And this brings us to a formal definition. Our source attributes it to Pierre Simon Laplace back in 1795. The theoretical probability of an event, let's call it E, often written as P of E, is the number of outcomes that are favorable to E, divided by the total number of possible outcomes.
So it's basically a fraction. On top, you count the outcomes you're specifically looking for, and on the bottom, you count all the possible outcomes. But, and this is a big but, this formula only works when we're confident that all those possible outcomes are equally likely.
Precisely. And the source then gives us some really interesting historical context. It wasn't like probability just appeared out of nowhere. These ideas can be traced back to the 16th century with a guy named J. Cartan who was studying the math behind games of chance.
Games of chance. So is it fair to say this whole field kind of grew out of people trying to figure out the odds in gambling?
It certainly has roots there. And the source highlights that over the centuries, some of the brightest mathematical minds got drawn to these questions. People like James Bernoulli et de Moivre, and of course Laplace himself. His 1812 work, Théorie analytique des probabilités, is considered a landmark. What's remarkable is how far-reaching probability has become. From biology and economics to genetics, physics, even sociology, it's an essential tool.
Wow. From figuring out dice rolls to understanding the economy and even the building blocks of life, that's quite a journey. So we've got this basic definition: probability of E equals favorable outcomes divided by total possible outcomes, assuming they're all equally likely. Let's look at some examples from our source to see how this works in practice.
A perfect starting point is our good old coin toss. Example 1 asks us to find the probability of getting heads when you flip a coin once, and then the probability of getting tails.
Okay, so when you flip a coin once, there are only two possible outcomes, right? Heads or tails. If we're looking for the probability of getting heads, there's only one outcome that matches that. So using our formula, it's one favorable outcome divided by two total outcomes, giving us a probability of 12. Same logic applies to getting tails, 12 probability.
Exactly. Now, example 2 throws in a little more variety. We have a bag with a red ball, a blue ball, and a yellow ball, all the same size and texture. Someone named Kritika reaches in and picks a ball without looking. What's the probability she picks yellow, red, or blue?
All right, so there are three possible outcomes here. She could pick yellow, red, or blue. Since it's a random pick, we're assuming each ball has an equal chance. So if we're picking yellow, there's one favorable outcome, the yellow ball, out of a total of 3. That gives us a probability of 13. Same reasoning for red 13 and for blue 13.
And this example leads to an important definition from the source. An event that consists of only one outcome is called an elementary event.
Yeah.
So like in our coin toss, getting heads is an elementary event, getting tails is another one. And in the ball example, picking yellow, red, or blue, those are all separate elementary events.
And here's a cool thing our source points out. If you take all the elementary events in an experiment and add up their probabilities, you always get 1.
Always.
So for our coin toss, 12 probability of heads plus 12 probability of tails equals 1. For the balls, 13 yellow plus 13 red plus 13 blue also equals 1. Kind of makes sense, right? I mean, one of those things has to happen.
It's a fundamental property of probability.
Okay.
Example 3 shifts gears to rolling a single die, a standard 6-sided one. First, what's the probability of getting a number greater than 4? And then what's the probability of getting a number less than or equal to 4?
All right, when you roll a die, there are 6 possible outcomes. 1, 2, 3, 4, 5, and 6. For getting a number greater than 4, the only ones that fit are 5 and 6. 2 favorable outcomes, so the probability is 2 divided by 6, which simplifies to 13.
And for getting a number less than or equal to 4, we get a 1, 2, 3, or 4. That's 4 favorable outcomes. Probability is 4 out of 6, simplifying to 23. The source also notes that these events, getting a number greater than $4 and getting a number less than or equal to 4, those aren't elementary events because each one covers more than a single outcome.
Right, makes sense. And this brings us to another helpful concept, complementary events. In our die example, getting a number that's not greater than 4 is the same as getting a number less than or equal to 4, and vice versa. The source uses this notation E bar to represent the complement of an event E. So basically, not E. And they give us this important rule. The probability of E plus the probability of not E equals 1. Or you can flip it around and say the probability of not E equals 1 minus the probability of E.
Super useful. If you can figure out the probability of something happening, you automatically know the probability of it not happening. Just subtract from 1. Like with our die, the probability of rolling greater than 4 was 13, and the probability of rolling less than or equal to 4 was 23. And yep, 13 plus 23 equals 1.
Nice and neat. Okay. The source then moves on to impossible and sure events. Let's think about this. What's the probability of rolling an 8 on a standard 6-sided die?
Well, a standard die only goes up to 6, so rolling an 8 is simply impossible. There are 0 favorable outcomes out of 6 possibilities. Probability is 0.6, which is just 0. The source calls this an impossible event.
Makes sense. You can't roll an 8 if there's no 8 on the die. What about the probability of rolling a number less than 7 on that same die?
Now, every single face on the die, 1 through 6, is less than 7. So all 6 outcomes are favorable. Probability is 66, which is 1. This is a sure event or a certain event, as our source also calls it.
So a probability of 0 means it absolutely won't happen, and a probability of 1 means it's guaranteed to happen, and the source sums it up nicely. The probability of any event is always going to be somewhere between 0 and 1, including 0 and 1 themselves.
Right. Now let's jump into an example with playing cards, something most people have at least seen before. Example 4 asks about drawing an ace from a standard deck of 52 cards. First, the probability of drawing an ace, and then the probability of not drawing an ace.
Okay, so reminder. A standard deck has 52 cards, divided into 4 suits: spades, hearts, diamonds, and clubs. Each suit has 13 cards: ace, king, queen, jack, and then the numbered cards from 10 down to 2. So to find the probability of drawing an ace, we need to know how many aces are in the deck. There are 4, 1 in each suit. So the probability is 4 favorable outcomes, the aces, divided by 52 total outcomes. That simplifies to 452 or 113.
And for the probability of not getting an ace, we can count up all the cards that aren't aces. That would be 52 total cards minus the 4 aces, leaving us with 48 non-ace cards. So 4852 simplifies to 1213. But remember that handy complement rule?
Yeah.
Not drawing an ace is the opposite or the complement of drawing an ace.
Yeah.
So we can just, the probability of not drawing an ace is 1 minus the probability of drawing an ace. 1 minus 113, which is 1213. Same answer, just a bit quicker.
I love those shortcuts. Okay. Example 5 takes us out of the world of games and into a real-world scenario. A tennis match between Sangeeta and Reshma. We know the probability of Sangeeta winning is 0.62. What's the probability of Reshma winning?
All right, well, in a one-on-one match like this, assuming no ties, of course, one of two things has to happen. Either Sangeeta wins or Reshma wins. Those are the only possibilities, and they can't both happen at the same time. They're complementary events. So Sangeeta's winning probability is 0.62. Reshma's must be 1 minus 0.62, which is 0.38.
Makes sense. The complement rule comes in handy again. Example 6 brings us something a little more everyday. Savita and Hamida are friends. Ignoring leap years for simplicity, what's the probability they have different birthdays, and what's the probability they share the same birthday?
Okay, so Savita's birthday could be any one of the 365 days of the year. For Hamida to have a different birthday, it has to be one of the other 364 days. If we assume all 365 days are equally likely for a birthday, which is a reasonable assumption, the probability of Hamida having a different birthday is 364 out of 365.
That sounds like a really high probability.
It is. It's about 0.997. And to find the probability they have the same birthday, we can use our friend the complement rule again. Having the same birthday is the complement of having different birthdays. So the probability of them sharing a birthday is 1 minus the probability of them having different birthdays, which is 1 minus 364, 365, giving us a probability of 1365.
So that's much smaller.
It is. It works out to roughly 0.0027, less than 1%. This is actually tied to something called the birthday paradox, which shows that in a group of just 23 people, the probability of at least 2 people sharing a birthday is actually greater than 50%. It seems weird because we tend to think about our own birthday compared to others, instead of looking at all the possible pairs within a group.
Wow, so the chances of any 2 specific people having the same birthday are low,
Yeah.
but when you look at a group, it gets much more likely that some pair will share a birthday.
That's
Super
right.
cool. Okay. Example 7 takes us to a classroom. 40 students, 25 girls, and 15 boys. The teacher's picking a class representative randomly by drawing a name card. What's the probability the student picked is a girl, and what's the probability it's a boy?
All right, so with 40 students, there are 40 possible outcomes when a name is drawn. For picking a girl, there are 25 favorable outcomes, the 25 girls, so the probability is 2540, which simplifies to 58. And for picking a boy, 15 favorable outcomes, giving us 1540, which simplifies to 38. Notice again the probability of picking a girl plus the probability of picking a boy equals 1, because those are complementary events. The representative has to be either a girl or a boy.
Right. Okay, example 8 involves a box of marbles. 3 blue, 2 white, and 4 red. 1 marble is drawn randomly. What's the probability it's white? What's the probability it's blue? And what's the probability it's red?
First, we need to know the total number of marbles. 3 blue plus 2 white plus 4 red gives us 9 marbles total. For drawing a white marble, there are 2 white marbles. So the probability is 2 favorable outcomes divided by 9 total outcomes, 29. For a blue marble, 3 blue marbles. So probability is 39, which simplifies to 13. And for a red marble, 4 red marbles. Probability is 49. And you'll notice, if we add those 3 probabilities together, 29 plus 39 plus 49, we get 99, which equals 1. Shows that principle again. When you add up the probabilities of all the possible outcomes, it always equals 1. In this case, the marble has to be either white, blue, or red.
Okay. Example 9 asks us to think about tossing 2 different coins at the same time. What's the probability of getting at least 1 heads?
When you toss 2 coins, there are 4 possible outcomes. all equally likely. Heads, 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 tails, tails, heads, and tails, tails. To get at least one heads, that includes heads, 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 tails, and tails, heads. 3 favorable outcomes out of 4 total. So the probability of getting at least one heads is 34.
And our source points out that we could use the complement rule here too. The opposite of getting at least one heads is getting no heads at all, which means both coins have to land tails. That's only one possible outcome out of 4. So the probability of getting no heads is 14, and the probability of getting at least one heads is 1 minus 14, which is 34.
Right. Sometimes it's easier to think about what you don't want to happen and then subtract from 1, especially when the event you're interested in has many different ways it could occur.
Yeah, that makes sense. Now, our source briefly mentions situations where the number of possible outcomes isn't a nice, neat number you can count, like the musical chair game and the missing helicopter example.
These examples are interesting because they introduce the idea of continuous outcomes instead of just flipping a coin or rolling a die.
Right. It's like moving from a world of separate, distinct possibilities to a world where things can happen along a whole range. So in the musical chair game, example 10, the music can stop at any point within a 2-minute interval. And the probability of it stopping within the first half minute is shown as a ratio. The length of that favorable time, 0.5 minutes, divided by the total possible time, 2 minutes, giving us a probability of 0.52 or 14.
And in example 11, with the missing helicopter, they assume the helicopter could have crashed anywhere within a certain rectangular area. And the probability of it being in a specific lake within that area is the ratio of the lake's area to the total area, which works out to 527.
So in these continuous scenarios, probability isn't about counting individual items. It's about comparing proportions of things like time lengths or area. Our source mentions that the exact definition of probability needs to be tweaked a bit to handle these cases rigorously. But these examples give us a good general idea.
Then we have example 12, which puts probability in a real-world business context. A carton has 100 shirts. 88 are good. 8 have minor defects and 4 have major defects. Jimmy will only accept a perfect shirt, while Sujatha will accept anything that doesn't have a major defect. If a shirt is randomly picked, what's the probability Jimmy will accept it? And what about Sujatha?
For Jimmy, it has to be one of the 88 good shirts out of 100 total. So his probability of accepting a shirt is 88 100 or 0.88. Sujatha is a little less picky. She'll take anything without a major defect. That means 96 shirts work for her. The 88 good ones plus the 8 with minor defects. So her probability of accepting a shirt is 96 100 or 0.96.
And finally, example 13 has us rolling 2 dice, 1 blue, 1 gray. At the same time, we got to find the probability of their sum being 8, and the probability of their sum being 13, and finally the probability of their sum being less than or equal to 12.
All right, so with 2 dice, we got to think about all the combinations. Each die has 6 sides, so there are 6 times 6 or 36 possible outcomes. You can even picture them as pairs, like 2 on the blue die, 6 on the gray die. For the sum to be 8, the pairs that work are 2 and 6, 3, and 5, 4, and 4, 5, and 3, and 6 and 2. 5 favorable outcomes out of 36 total. So the probability of the sum being 8 is 536.
Now, for the sum being 13, think about it. The highest number on each die is 6. So the highest possible sum you can get is 6 plus 6, which is 12.
Ah, so getting a 13 is impossible.
Exactly. 0 favorable outcomes out of 36. Probability is 0.36, which is 0. It's an impossible event.
Just like rolling an 8 on a single die. And lastly, what about the sum being less than or equal to 12? Well, as we just said, 12 is the highest sum you can get.
Meaning every single one of the 36 outcomes will have a sum less than or equal to 12.
So 36 favorable outcomes out of 36 total. Probability is 3 and 636, which equals 1. A sure event.
And that wraps up the examples from our source material. The source then gives us a helpful recap in exercise 14.1, question 1, summarizing those key principles we've been talking about.
Yeah, it reminds us that for any event, the chance of it happening plus the chance of it not happening always adds up to 1. The probability of something impossible is 0. And the probability of something that's certain to happen is 1. And when we look at all those basic single outcome events, the elementary events, their probabilities have to add up to 1 as well. And of course, the probability of any event is always going to be between 0 and 1, including 0 and 1 themselves. These are like the ground rules for theoretical probability, at least when we can assume all outcomes are equally likely.
So as we wrap up this deep dive into probability,
Yeah.
what stands out to you as the biggest takeaway?
I think it's that probability gives us a really logical way to approach uncertainty, at least when we're dealing with scenarios where all the possibilities have an equal chance of happening. And that simple formula, favorable outcomes over total outcomes, along with those concepts of complementary events and the probability scale from 0 to 1, It's amazing how widely applicable these ideas are, from simple games to all sorts of real-world situations.
Absolutely. It's, like you said earlier, that feeling of uncertainty when you flip a coin or roll a die. There's an underlying order to it that probability helps us understand. It's not just random chaos.
Exactly. So now that you've got a good grasp of these fundamentals, I'm curious, what happens when you start thinking about situations where the outcomes might not be equally likely? What new wrinkles and challenges come up when you can't just count those simple possibilities?
Hmm. That's a great question. And a solid understanding of these basics sets you up to explore those more complex ideas down the road.
It definitely does. So, to you, our listener, thanks for joining us on this deep dive into the fascinating world of probability. We hope you found it insightful and maybe even a little bit eye opening.
And we encourage you to look around and see if you can spot examples of probability in your everyday life. You might be surprised how often they pop up.
It's all around us if you know where to look.
It really is.
Thanks again for listening.
Until next time.